if it's working. Okay, looks like we're here. Let me know if you're in the chat. Okay. Let me know if the audio is all fine and if you hear me. Looks like we got 2 people so far. And as you might have noticed, I'm not Natalie. So I'll be doing today's lesson, and Natalie will be teaching on Wednesday. It might be a dual lesson again, so I might be there as well. So we'll see what happens, but we're just gonna let everybody roll in. So we'll just wait a few minutes. Hi, David. As I just wait a few more minutes, I'll just talk about... Hi, Natalie. I'll just talk about the, in general, just what we're going to talk about today. So, this lesson's going to be a lot of, like, back-end stuff. Not really much with gameplay, but different things you could use to make various systems. Nice tools just to know about as you go along developing games. So these things are, we have lists, stacks, queues, static methods, and then the biggest thing, recursion. Recursion's a bit complicated, so I'm going to be spending quite a bit of time on that. Oh, hi Emmy. Looks like you're here too. Looks like we have a lot of people, so I guess we'll just start. And Emmy, if you weren't here when I said in the beginning, I'll be doing today's lesson obviously, and on Wednesday it will be Natalie, or me and Natalie. It might be another dual lesson, but we'll see what happens. So the first thing we're going to talk about is recursion. So, what is recursion? So, recursion's a bit complicated, so I'm going to spend quite a bit of time on it. But essentially, recursion is just is calling a function within a function. So, I have this bit of code. Oh, not this. This. Okay, I have this little bit of code here, and I also have a picture right here. So hopefully I can explain this nice and simple for you. So right here we have Russian dolls. So if you know Russian dolls, you open them, and then inside the Russian doll is another Russian doll. So what does this have to do with recursion? So essentially what we're going to do is we have a function, and the function over here is going to, this is written a bit differently from how you guys would write it, but this is just a function called openDoll, and it takes an argument called doll. So doll would just be a type, so you could just think of it that way. So think of it as a doll is a game object, and then if that game object has a function that returns is empty, so if nothing, I'm going to restart. So this game object, the Russian doll, has various functions in it, and one of them keeps track of whether or not it has another doll in it. So the first one has a doll in it, because this one fits in it, then the next one, and so on, up until you get to the last one. Now the last doll is not going to have anything in it, so it's going to return is empty is false. I mean, is true, because it doesn't have anything in it. This one will be is empty is false, because it has another doll in it. So the reason I'm telling you this is because if you look here in the function, we call this function, I should do a different color, let's do red. We call this function inside of the same function. So what we do is this function essentially is going to return, well, actually I guess it doesn't return anything, but it's going to stop running once it reaches the last doll. So if I was going to write this function myself, or if this was a more feasible situation, this function would return something, which would be the doll. So let's say you wanted to find which doll is the last doll. You do function, whatever type the doll is. So function doll, and then the name of it open doll. Then it takes an argument doll. So I know that's a lot to take in right there, but what it's going to do is it's going to check the first doll. It's going to see, is it empty? It's not empty. So then it goes to the next line of code, which is doll.open. So what that does is it goes to the next doll, and it calls the function with the next doll. So the first time you call this function, doll is equal to... Oh, not that. Okay. Doll is equal to this one. So then when you call the next function, we're going to take the one that's inside of it. So now we're doing open doll, then this one. And then this one is not empty because it has this one. So then we're calling the same function, but with this one as doll over here. That one's not the last one, so on, blah, blah, blah. Up until you get to this one. Then when you call the function with this one doesn't have any more to go through. So essentially what I would do here, I would add a little bracket here, and then this would say in here, doll, because we're going to return the doll that doesn't have anything in it, so the last doll, and we're just going to say return doll. Oh, okay. So I know it's a bit jank right there. So hopefully you guys understand it, but basically recursion is just calling a function within a function. Now there are a couple of things you need to keep in mind with recursion, is making sure it doesn't infinitely run, because then you'll just crash your game. So let's say that, like, I know this doesn't make sense like in a real situation, but let's say in a game situation where this could be possible. You have this doll, well, this doll inside of this doll inside of this doll. But let's say this doll was inside of this doll. Now I know in real life obviously it wouldn't fit in there, but if you're talking about a game, like, this is just a data type, so you could just put that doll in there. So technically you could put this doll inside of this one. If you ran this function recursively, it would never end, so that your game will just pause indefinitely, and you'll have to Alt F4 the game, just force close it, because the game will just not run. Because it's just going to be infinitely running through this function, this recursion function, and never actually reach an endpoint. So that's one thing you have to keep track of, and I'll just explain it again just because this is a complicated subject. So if I had this one inside of this one, and the other ones were as they should be, so I call this function, it opens it goes to this one. This one is not the last one, so it goes to this one. I open it, I go to this one. This one's not the last one, it goes to this one. I open it, goes to this one. That's not the last one, so it goes back here. So as you see, it never ends, if that was the case, where this one was inside of this one. So that's just my hypothetical situation, where that's something you always have to make sure of, because you'll just crash your game. So, and that's not good, especially if you didn't save, because if you didn't save, you're gonna lose all your progress, because you can't stop Unity, because it's just gonna be infinitely running through this loop, and it won't let you stop Unity. So you'll have to forcibly close it, which means you can't save your progress. So that's my first example. Second example, we have a grocery list. So imagine this. You have your grocery list, and you have a function that's just like, go to this store and get whatever item is on this list. Now there's a couple things that go along with this. First you have to see, is there meat? Like, do they have what I'm looking for? In the first case, it would be meat. Yeah, that's pretty much it. And then you have to bring it home. So one reason why you might want to use recursion is because... So you have... Okay. We'll just explain it, the hypothetical situation. So you have a function that's just like, okay, let's go to the store and see if they have meat. If they have meat, let's bring it home. Well, let's buy it and bring it home. And then you go to the next item on the list. Okay, so now if vegetables... Well, okay, let's go to the store. If they have vegetables, I want to buy it. Go home. Then go to the next thing. Go to the store. Do they have tin food? If they do, buy it. Go back home. Obviously, this doesn't make sense, because why would you go home just to go back to the store to see if they have the next item on the list? So this might be an instance where you might want to use recursion, Because what you could do, you go to the store once. So you go to the store, and then you're just like, okay, do they have meat? If they do, buy it. You buy it, and then you go to the next item on the list. You would call the same function, which would be this function in this hypothetical situation, would be, do they have food? And then if they do, put it in your cart. So the first thing you do is go to the store. Then you call the function. You would call the recursion function. That would be check for all these things, see if they have it. If they do have it, add it to the cart. So you go to the store. Do they have meat? Yes, they have meat. Add it to the cart. Do they have vegetables? Yes, they have vegetables. Go to the cart. Do they have tin food? Maybe not. If they don't, go to the next item. Do they have fruit? Yes, blah, blah, blah. And then after that, once the recursion's all over, because you've ran through every element, you would be like, okay, great. Now, let's buy it and go home. So, that might be another instance where you might want to use recursion. In this case, you could also technically use a for loop and just run through each element here. But as with programming, there's multiple ways to do the same thing. Sometimes some ways are better than others. But just knowing, I just want you to know that recursion is a thing. And the last thing I want to do is this last thing here. This will be the last bit of recursion I talk about. Okay, we'll start here. So you have this point here, and you have a point here. Actually, let's make this one green. Okay, so you have your 2 points, and you want to reach the endpoint. Let's say you have all these points, just like this, all over the place. And then we're just going to connect them. See how this goes, blah, blah, blah. Beautiful. Yep, do that and that. Okay, now this is a prime example of why you want to use recursion. Some of the others, like this one, like I said, you can use a for loop. But this one, a for loop wouldn't really work because this is a bit more dynamic and you don't have that much control over the various elements regarding this. So if you wanted to find the shortest path or a path, let's do a path to make it less complicated. You want to find a path to reach the endpoint going from circle to circle. And you could only go circle to circle. Oh, hello. Looks like we got a new member. Okay, so go circle to circle, and we're going to record that as we go along and find the endpoint. So, why do you use recursion for this? Because in here, we have a point. This point has one, we'll call it a neighbor. It has one neighbor. So, because it only has one neighbor, it has to go to this point. So, when it's at this point, it now has 2 neighbors. So, this is why we're going to use recursion. Because we're going to have a for loop of our neighbors. So, we have our first neighbor, and we're going to put that in the for loop. So, then we go here, and then we're going to recursion. So, we're going to use recursion. We're going to call the function again. And the function for recursion is just going to be to go to the next neighbor. And each time it goes to a next neighbor, it's going to check to see if it's the endpoint. So this endpoint, hypothetically, would have a variable that's like, okay, this is the endpoint. But I digress. So it's going to call the recursion. It's going to see it. It's going to go through each of its neighbors, see if it's the endpoint. If it's not the endpoint, go to the next neighbor. So we're going to go here. You got the sprites. I don't know what that means. I don't know what that means, Tayshawn. Okay, but I'll carry on. Okay, so we're at this point. So it has 2 neighbors now. So we're going to go in order. Oh, okay, it's for Natalie. Okay, my bad. So it has 2 neighbors. We're going to go to the first neighbor. And as you see, we're skipping over this one because we're going to this one first. Now this one, we're going to see, is this the endpoint? It's not the endpoint, so we're going to go to the next neighbor. And now this neighbor has 3 neighbors. Sorry for saying neighbors a lot, but so this point has 3 neighbors. So now we're going to go to the next one. So let's say it's this one. So this is the path we're taking so far. It's going like this. and then as it goes through the neighbors, blah blah blah, eventually it'll reach the endpoint. But this isn't necessarily the shortest point. So this is why you want recursion, because recursion, after it would find this path, it would then go back, because yes, it would go back, and then it would check all the viable options it has. So technically, it would go back here, and then it would be like, okay, can I go this way, and then this way? But it's like, okay, no, because I've already been here. So it backtracks again, blah, blah, blah. But you need to do recursion for that, because think of it as each time you reach another node, let's call these circles nodes, you're going to have to call another for loop. Because, like, each neighbor, so it has two neighbors, so you run a for loop with two neighbors. You can't dynamically do that unless you do recursion, or you hard code it so that you have a for loop for each neighbor. But even if you have this little amount of neighbors, that's going to be way too much. Like, I promise that'll be like way more than 1,000 lines of code of just for loops. But by doing recursion, this for loop is going to go through element 0, which would be go this way. And then once it filtered out all the viable paths for this way, so I'm just going to erase some of this. Eraser. So let's say this path doesn't go anywhere. So I broke the point there. So in this recursion, we're going here. It has two neighbors. We're going here. This is not the endpoint, and it has nowhere to go. So because it has nowhere to go, we're going to go back, and then we're going to go to the next element of the for loop, which would be element 1. Then it would go here. And then after that, now there's 3. So now we have another for loop. Well, actually there's 4, because the last one we went to. So this one now has 4 nodes we could go to. But we'll skip this one because we just came from this location. So theoretically, we would tag it to say, I've been here already. But then you would also run through these in the for loop. That's like, okay, let me check this way. This way will eventually reach the destination. Then I go back, go to the next element of the array, 1, go back, okay, I found it, and so on. So, recursion, just like with how I'm doing now, it's just a ton of repetition. It's doing the same thing over and over, but it's basically a good way to dynamically use for loops. So it's like for loops inside of for loops, blah, blah, blah. Because you go here, this is a for loop, then let's say this node went, oh, that's really big, but whatever. Let's say it goes here. Now here's another for loop. So then it goes from 0, okay, it reaches it. Now it's index at 1, goes here. Okay, it reached the end of the for loop, we'll go back. Now this one is at index 1, because it just ran through index 0, so then it goes here. So on. So, I'm not going to talk too heavily about what I wrote here, because it's way too complicated, but I just want to show you just a little bit of something I did because I use recursion here. So I have get all paths, and then you see I use get all paths again here. So I'm calling the function within itself, and basically what I'm doing is this exact thing I just talked about here. Actually, where was it? Oh, here. Where I just go to each node, and I try to find a path. So in the project here, it's not the prettiest, it's just a demo. If you hit play, and so it's going to go to this node. This is a node, just like in the example. Oop, nope, okay. Just like in here. Each of the dots are a different node. And each of the nodes, oh god. Each of the nodes have different paths they could go. And if I hit K, it's going to bring up all these things here in the console. And these are the various paths that it could take to reach an endpoint. So in this hypothetical, when I press K, I'm telling it, find me a path to reach the kitchen. So the kitchen is indicated by this purple box. So currently there's 3 points in the kitchen. So I'm like, okay, find me a path to get to the kitchen. So these are all the paths it went through in order to find a path to the kitchen. And as you can see, there's a lot. And then at the bottom, you'll see that there's 2 different paths. There's path 1 and path 2. So path 1 is based on, actually I forget which one's which, but one of the paths is based on the node I just came from. and the path and the node I'm currently going to. So if you look here, the path we have is 3, 4, 5. So 3 is this one here, then it goes to 4, and then it goes to 5. So the path would be go here, here, and then here. And then the next path I have is path 1, which would be the path I'm currently going to. So this one just skips a step. Instead of going from here to here, since I'm already moving towards this node, I'm just going to go right there. And then it goes to node 5, which is this one. So as you can see, the path then goes here to here. Go back to the code. So I'm recursively doing this, but I have this for loop here. And in the for loop, I check to see, am I at the location I want to be at? So in this situation, it's am I in the kitchen? Is this node the kitchen? Which I have, the wrong one. These nodes I have tagged as kitchen here. So each of the nodes have the kitchen tag. So that's what that is. So I'm checking to see, is the current node I'm at the location I'm looking for? So I'm running through each of the neighbors. Here's the if statement. If this is the location I'm looking for, then I add the path to, it's a stack. We're going to explain that in a sec. But I add the path to a stack. But if it's not the location I'm looking for, then I add the neighbor to the stack, and then based on that neighbor, so I then go to that neighbor node, then I run the same function over again. So basically, I'm looking for all the paths that that neighbor can then take to hopefully reach the endpoint. So that's my spiel on on recursion. This is a lot of complicated stuff. I'm not going to go in depth about it. I just want to get the general gist of it. Basically, well, I'll also say this. So this returns a list. So then at the end, I just return all the paths that reach the location I'm looking for. Because as I run through it, if it's the location I'm looking for, I add that path to the path stack I have, and I return the paths. So, as I said, this is a big concept, but I just want you to know about it. I don't expect you to know how to use it, like expert level. Obviously not. I just want you to know it exists. Just knowing it exists is one step towards the right thing. What are nodes? Okay, so nodes, I made these myself. So this is not like a built-in thing. This is just a class I made called a node. And the node doesn't really do much besides store things. So in this case, the nodes, they store its position. So I tell it, if I'm looking for a position, I just do nodes.getPosition, and it'll return the position. It stores the location it's at. These various things. Yeah, but as I said, nodes are something I made. So don't be like, oh, like what are nodes? The nodes are they just represent different points I'm looking for the player to navigate through this environment. So this is the player. So the player navigates to the different nodes. If I hit play, he's moving towards the node, and so on. But in my situation, the nodes basically just store information. They don't really do much besides that. So if I go back here, and I go here, I check to see, where is it? Here we go. So neighbors at I, this is a node. So like, go back here. So this neighbor, the first one in its for loop would be node 3, which is this one. So I say, is this node, is its location the kitchen? Then go back here. If it is the kitchen, then I'm going to add that path to my stack, which again I'll explain later in just a bit. If it's not, then I recursively call it again to continue going through each of the nodes to find the location I'm looking for. So, okay, so hopefully you got that, or just the general gist of it. That's my main focus. I just want you to know what recursion is and the general gist of how it works, because then in the future you might want to try to use it. But this little thing I have here is probably too complicated to explain in this sitting, so I'm not going to. But that's the general gist of how I use recursion in something I'm doing right now to find a path and etc. And hopefully these little examples I talked about here and this little bit of code here just hopefully makes sense to you. But the next thing we'll talk about is lists. Whoa. So lists are a magical thing. So if you remember, a couple of weeks ago, I talked about arrays. So when you have an array, it just stores a bunch of data pretty much. But the thing about arrays is that you have to set a specific size to the array. And once you set that size, you cannot change it. So in this case, this raycast, this array of raycasts is 20 elements big. So that means it could only store up to 20 elements. It cannot store 21 elements, only up to 20. Well, actually, technically, it allocates data for up to 20, but even if you don't store 20 things in it, it still has data set aside for those 20. But you don't need to know that. but okay, so that's the thing about arrays, is that they have a specific size. A list is basically just an array, but it does not have a specific size. Now, there is a downside to lists, and that is you cannot, how can I explain this? So lists, when you add an element to a list, that element, that piece of data is stored in the next free location on your computer. So I know we're getting a little back-end here, but just knowing the back-end stuff makes this make a bit more sense, so I'm going to explain it. So the next free bit of data is where it'll store the next thing you add to this list. So that could be before or after the last element you put in the list. So let's say, we'll go down here. You have element here, here, here. So here's computer data over here. Some more computer data over here. So this one is free. Here's the first thing I'm going to add to the list. Then we add something here. Then we add something here. But then let's say the next thing we add to the list, we had something be deleted in this piece of computer data over here. So now this piece of data is open. The list is going to put that data over here now. So as you can see, the list is not ordered in any specific way. The list will put data wherever it wants, but it's dynamic. So that's the upside. If you just want to continually add things to it, you can. That's the upside about a list. The downside is that it puts it wherever you want. So if you have things in a specific order or specific places, it won't work. I don't have the project brought up now, but if you remember a few weeks ago when I showed you the project where I was explaining lists. Oh, bye Tayshawn. I had a lot of things happen specifically based on the index of each list. So I had the character. So the character name, let's say MC, that's the character's name. Let's say MC is at index 0. Then I had the color based on her, also on index 0. I had her little picture or whatever also on index 0 in a different array. That type of logic won't work with lists because it'll just store the data wherever it wants. But like I said, lists are also good because it's dynamic. So now I'll actually... Okay, that wasn't English. Now I'll actually explain where and how to use a list. So in this situation, if you remember in this project, which is the project me and Natalie are currently working on, let's hit play, start the game, wait for it to load. Okay, hit play. So if you walk up to a zombie, you'll see this meter, the image slowly get bigger as I move towards the enemy. So what does this have to do with lists? So basically, where is it? Okay. Actually, I'll just leave this open. So as I walk towards enemies, I have them added to my list. And then what I do after that is I run through the list, because it doesn't really matter what order I run it through. I'm just checking to see which zombie is closest to me. So as an enemy enters my radius, I add that zombie to my list, and then I run through the list. I see which one is closest to me, and then based on which one is closest to me, I change the opacity of the pressure, like the little UI thing I showed you. So, like I change that UI, the opacity of that, dependent on how close I am to the closest zombie. So obviously you wouldn't want it to be fully black if one of the zombies within your range is far away. You want it to be based on which one is closest to you, because otherwise it wouldn't make sense. Hopefully that makes sense. Because let's say you have 3 zombies within your range. One of them's really far away, one of them's really close, and one of them's in the middle. Let's say you just check the one that's furthest away. The opacity wouldn't be that high because the enemy's further away from you. You want it to be based on which one is closest to you, because that's the one that's stressing you out the most currently. So that's the little gist of that. So that's why I use a list, because as I said, it's dynamic. As let's see if I can find it. As enemies enter a collider, I add them to my list. Actually, I'll just double click on this. Where is it? Okay, this one. Let's see where I use it. Okay, so as the zombies enter my trigger, I do enemies.add. So doing .add will add it to the list. So I have a list of game objects. So as you can see, it's a list. The greater than symbol game objects, less than symbol enemies. I do go back down here. So enemies.add, and then I'm adding that game object to my list. You could also see up here, I do enemies.contains. That's to see, you could check each element of the list to see if it has something based on the argument you give it. So basically I'm like, okay, if a zombie enters my trigger, is the zombie already in my trigger? Otherwise, don't add it again, because you only want it to be added once. Because you don't want it to be added more than once, because that doesn't make sense. So if it's not already in my list, add it to the list. And then once something exits my trigger, I do enemies.remove, and then other.gameObject. So the thing that's leaving my trigger, I'm checking to see, is it an enemy? If it is an enemy, I also check to see if I'm colliding with the trigger. That doesn't matter for this situation. I check to see, is this enemy currently within my list? So other.gameObject. So the thing I'm colliding with, if that thing is in my list, then remove it because it just exited my trigger. Yeah. And then at the end here, I'm just like, if there's no more zombies in my list, just set the opacity to 0 because there's no enemies within range. And then the last bit of logic I do with this is, let's see if I can find it, up here. So up here I do a for each loop. If you remember a few weeks ago or last week, I forget, I talked about the difference between a for loop and a for each loop. In general, you don't really use for loops that much with lists. You can, but since they're not ordered, it doesn't really matter that much. But a for each loop, it'll just run through each element of your list. So I explained this already, but I'll explain it again. With a for each loop, you put a data type. So since I have a list of game objects, we're just going to do game object. G could be anything. I could change the name of this. It doesn't matter. But I call it just G for game object. Then you just type in and then enemies, because the enemy is the list. So enemies is the list. So I'm running through each game object in the enemy list. And then I basically compare each of their distances to see which one's the closest. And then based on how close the closest one is to you, I change the opacity down here of that UI element. So that's why you would use a list. I can't really do that with an array because I don't really know how many enemies are going to be entering my collider. So technically though, one more thing I should explain. In theory, technically, you could have an array of, let's see, 1, 2, 3, 4, 5, 6, 7. So the 7 zombies currently in the world. You can just start the game off with an array of 7 and then just add and remove things to that array as you see fit. Yeah, that works, but the reason why you wouldn't do that is because, let's say, I'm balancing the game, or as David said last week, you have different difficulties. So let's say I add and remove different zombies to this world based on those difficulties. That function isn't going to work anymore because, well, that array. Because now I've changed the sizes of the array. It's easier to just have a list and have it be dynamic than to specifically set it in the beginning, since if you set it at the beginning, that's the hard set number. If you ever change it in the future, you have to remember to go back and change it in that array. So it's always good to have things be dynamic, but like I said, I'm not sure how much you care about this. For each loops are technically 6 times slower than a for loop. But you probably don't care about that for your projects because your projects aren't to scale that this would really matter. But technically it would run through an array faster. But technically you could also use a list with the for loop. So a lot of contradictions here. But like I said, that's the magic of programming. There's like 27 ways to do the same thing. So I'm just trying to show you all the different options you have, and hopefully you can pick and choose which ones you want based on your situation. But in this situation, I would heavily advise you use a list, because like I said, the lists are dynamic. This is a dynamic situation. In the future, I might want to add or remove zombies based on that. So that's my little spiel on lists. So now we'll talk about stacks and queues. Whoa. So we'll go here. So I'm not going to talk about the code here. I'm just going to show you just some of the wording that goes into it. So with a stack, here, don't let that's confusing. Look at this one. Okay. So I have a stack. I guess this one's also confusing. I'll write a new one for you guys. So we have a stack, and then like a list. So stacks and queues are basically just lists, but I'll explain why they're different in just a sec. So you do stack, and then just like in this other example I did, over here, you do the little bracket things, the greater than less than symbols, and then you put the data type in it. So we have collider, game object. So whatever data type you want, go back here. So this could be like an integer. So we're going to have a stack of integers, then you give it a name. Just say test. Okay, you made a stack. But I guess I should also say this for lists. There's one thing you always have to do, otherwise you'll get an error, and you'll be very confused as to why you have this error, because you would think it automatically does it for you, but it doesn't. So what you have to do is you have to make sure you set it equal to a new list, whatever. Okay, so since this is game object list, make sure when you make a new one, you set it equal to a new list game objects, and then you put these brackets at the end. And if you look here, these brackets are not here. So when you initialize it, you don't need the brackets. But when you set it equal to a new one, you do need the brackets. If you don't have that, you'll get an error. That's basically like, this stack was never created. This list was never created. And you'll be confused, because you'll be like, I did make it. It's right here. Why is it giving me an error? And if you look here, it won't tell you anything's wrong in the code. But when you hit play, it'll give you an error. So make sure when you make a list, stack, or a queue, you do this. Otherwise, you'll get an error. But that's that. Back to here. So you now do this. And just like with the list, you set it equal to a new one. Go here. Blah, blah, blah. Oh. Gotta do new stack. Boop. Okay. So that's how you make a new one. So what is a stack and what is a queue? So the way you could think about it, I should have brought up a picture, but I'll just draw it out, I guess. So let's make a new one. Oh no, I don't want that. Whatever. Oop. Oop. Okay, we're back. Okay, so a queue, you could think of a queue just like a regular queue. So queue spelled this way. Okay, that's how you spell queue. I think you should know what a queue is. It's basically the first one who's online goes first. So basically, if you have, here we go. If you have, wow, beautiful. Okay, you have a lemonade stand, and then somebody gets online. They're the first one online, and then you add a new person to the line. So now this person is here. So this person will be the second person to get their order taken. And so on. As you add things to a queue, they will always go in order of how you put them in. So a queue is dynamic, just like a list. It's not like an array where you have to define a specific size. But as you add things to it, it's in the order you put them in. So because this person was added to the line first, he's going to be the first one to leave the line. And then so on. A queue is the exact opposite. I mean, a stack. A stack is like a stack of papers. So you have paper. Here we go. That's paper. As you add paper to the stack, so here's the next one added. In order to get to the second piece of paper from the top, you have to remove the first piece of paper to get to the second one. So a stack is the last in, first out. Whereas a queue is first in, first out. Hopefully that makes sense. So a stack, as you add it, it gets added to the top. Whereas a queue, as you add it, it gets added to the back. Then when you remove it, the last one you removed, well, the last one you added is the first one to get removed. And with a queue, the first one to get added is the last one to get removed. No, wait. No, a stack. No. A queue, the first one to get added is the first one to get removed. A stack is the last one to get added, is the first one to get removed. Okay. That's the difference between those. Like I said, a list doesn't have any of these qualities. You could add and remove from a list, but they're in no specific order. A queue have these specific orders. So now, how do you do any of this? So here's a stack. So you have a stack. Let's say you wanted to add something to it. So you do test dot push, and then it'll put 5. So since this is an integer stack, I'm just going to add the integer 5. So what I do is test dot push 5. So basically, this is going to add 5 to my stack. If you remember with the list, I had to do whatever the list was named, dot add. Go back down here. Okay. I had to do enemies dot add in order to add something to a list. With a stack, you do test dot push. So if you remember, like I said, a stack is last in, first out. In order to check to see what's on top and actually gain access to whatever that variable is, you have to do test dot pop. Not pop, I lied. Dot peek. So if I ran like a debug dot log, okay. If I ran a debug and then I hit play, what this would do, this would print out 5. Because I add 5 to my stack, and now I'm peeking. I'm looking at the thing that's on top. Think of it like the paper. Okay. If I'm looking at a stack of paper, I'm going to peek at the paper, see what the first one on the stack is, what the top thing on the stack is. Then I'm going to print out what that actually is. So since the last one I put on was 5, it's going to print out 5. And then if you wanted to remove an element from the stack, you would do test dot pop. Dot pop. And then what this would do, this would remove 5. So if you see, I don't have to put anything in here. It doesn't take a data type because it goes in order based on the order you put it in. So pop is just going to remove the last thing you put in. So the downside to stacks and queues is that you can't get a specific element in the middle. So I can't be like, what's the bottom element on this stack? There's no way for me to get the bottom one without having to break down the stack in order to reach the bottom and see what the last one is. That's the downside to it, but the upside is that exact same thing. It's always going to be in this specific order. It's always going to be last in, first out, which is good for many situations. In my case, when I add the waypoints, I want the one on top to be the the last neighbor I added to the stack. So go back here. So once I add this to the stack, this one's on top. Then I see what's this one's neighbors. I go to this one because this is a neighbor because they could see it. I go to this one. I'm like, okay, what's the neighbors on this one? Because this one's on top of the stack, and so on. Now with a queue, the wording is slightly different. In order to initialize them, it's exactly the same as with a list and a stack. You do queue, int, test. Oh, I can't name it test. Test1 equals new queue int. Wow, okay. So this wording is exactly the same, but in order to do each of these things, it's slightly different, but they work essentially the same exact way. So we'll do test1 dot in queue 5. So with a queue, you have to do enqueue. That's the same as push. In the queue is just adding something to my queue. Queues work the same way as stacks in that you peek at them. So that's the same. In order to see what's first in the queue, you just do peek. As you can see, there's no errors. And then to remove an element from the queue, you do dequeue. And then that's that. Oh yeah, you don't need anything. So since it's in order, I just do dequeue, and then it just works. So whoa, that's great. So if you ever have a situation where it needs to be output in the same order it gets inputted, you would use a queue. And same as I was saying with the stack, that's each of their pros and cons with the stacks and queues and lists also. They each have their own purpose. They each have their own downsides. Same with arrays. I want you to know each of these exist because, I don't know, like, as you program, you're like, wow, I wish I could put this in order. But it's like, oh, you can. You just use a stack or a queue, depending on whatever your situation is. Or it's like, oh, I wish I had an array that I could just add things to. It's like, oh, you use a list. But you also just have to remember what the downsides and limitations to each of these things are, which hopefully I explained good to you, and that you understand. So, the last thing I want to talk about is static methods. Wow, static methods. Okay, so what's a static method? So as you can see here, I have pretty much everything in here. Even this class is a static, like this is a static class, this is a static method. So what does that actually mean? So with pretty much everything you've ever programmed so far, like it's never been static, it's just whatever. So the reason for that is that because none of these are static, each of these classes and functions, they're like its own specific thing. So each of these variables, and like they're saved within this specific class when you create it, and then you could change them real time, all these things. When you have a static class though, these are like one-time things. So if you need a function, static, here we go. So in this case, I have a static function for, I want to get the angle between 2 points. So the reason I use this is, as I turn to the next point, I want it to start moving once its rotation is okay. So I want it to start rotating, well, start moving once its rotation is within a certain like angle. So in this case, if I go here, that angle is 75. So once the way it's looking, based on this thing here, you can see the way it's looking. Once the way it's looking and the point it's moving to, once that angle is less than 75, I'm going to start moving towards it. Otherwise, if it's more than that, I'm just going to continue rotating without actually moving forward. So if you see here, actually let's just call it boop, boop. Okay, so as you can see, in this function, well, in this class, this is not the static class. I call this static function, I give it arguments, and then it returns a float, and then I put it in angle. So I just have this static function. It just does some math for me and just returns a number. Now technically, I can just like I can just make this. Yeah, let me do this. Oop. Copy. Like I can just make a function here, make it not static, and then call it in here. Like, yeah, I could do that. But let's say I wanted another object to call this function. I would then have to import waypoint navigation function so that they could reference this function from waypoint navigation from this class here. But if I go here, since it's static, every object in the game has access to these functions and to this class. I don't have to actually add it to anything. Like if you go up here, like I don't write equations, like the name of it, anywhere. I never import equations anywhere. If you look here, I just write equations and it's green because it's static. So it just knows it exists within the project. So making it static means anything could reference it. So you could just do some math. Like if you wanted to do some math that other functions might want access to, that's why you would want to make it static. Because instead of writing the same function in multiple classes or different scripts, you could just write it once, and then based on the numbers you put here, so the arguments you give it, it does math and then returns a number. Trying to think. Yeah, that's pretty much it. Like, there's not much to static. You just have to remember, I can't do something like this. I can't do int last num equals 0. Like, you'll see, it's just like, it gives me an error. And you might be like, why? Like, in these scripts, you could just write int test num equals 0. Like, see, this works fine, but then this gives you an error. That's because static classes don't store their own variables. They'll just run the code within each of their functions as you tell it to. These functions don't store anything. You can't tell them to store anything because they won't store anything. They're their own independent thing that you can use to just do some math and return a number. So they're helpful in their own ways. But like I said, the downside to this is you can't store it. But the upside is that everything can see it. So any script I have can call this function and it'll do the math based on this, and then it'll return the number, and then, whoa, great, you have the angle. Whoa. Okay. That's pretty much that. That's all I want to talk about with static. I don't use them all the time, but they're very helpful. If you ever have some math you just want to do that you use a lot, I would just make a static class. You just make a new script. At the beginning, add static to it. Oop. Add static to it. Then also, if you see here, I don't have mono behavior here. Static classes don't have these. So make sure you get rid of that. Otherwise, you'll be like, oh, why do I have an error? So make sure you get rid of that. And that's pretty much just how you create a static class. And then the static functions are pretty much exactly the same. You just write the function name, and then, like, okay, so I have a function here. You just do, like, static. It's like, oh, great. Now I have a static function. Although, as you can see, there's a bunch of errors there because that script wasn't built on having it be static, but this one is. So, that's a static class. Wow. Great. They're nice, I promise. But I'll repeat it one more time. So static functions and classes can be referenced anywhere within any script. It's magical. But they won't store any of the data you give it. So that's the upside and the downside to static whatever. The last thing I want to talk about, this is going to be super short, is as you can see I have this little monstrosity here. This is called a summary. And basically, this is like, doesn't do anything. It's basically just a comment. But it's good for when you're trying to reference things later in the script. So, where do I have this? So I'll go back here. Copy. I'll search for it here. Okay. So I have this here. If I highlight over it, you'll see I have this little text here that says get angle between where viewpoint actor is looking and a second point. Now, this was a function I made. So I made this. So you're like, okay, so where did that little definition come from? You could write your own definition here. And then as you highlight over it, it'll tell you what it does. So this is good if you ever need like a quick refresher on what one of the functions you wrote did. Or it could be like, if you're working with other people. This is the main point of it. If you're working with other people, they might not know what this function you did does. By having this summary there, they could just highlight over it. And then depending on how well written this summary is that you added, you could be like, they should just know what the function does because you told them what it does. So, it's nice. That's that. Like I said, not much to it. You just hover over it. Oh, here's another one. Rotates towards point. That's this one I have here. I can't really talk too much about that. It's as simple as that. That's all I wanted to say about summaries. They're helpful, especially if you're working with other people. If you continue wanting to be a programmer and you work with other people, they'll be very upset with you if you don't comment your stuff, because they just won't know what you're writing. Even if you write the best code, like it's beautiful, AAA, the best code you could ever have seen in your entire life. People don't want to try and diagnose what your function does to see what it does. They just want to look at it and be like, oh, here, it says here that this function rotates towards a... I guess I could be a bit more specific. Like, returns the angle... No, actually, I lied. This just rotates towards the point. This one is where it gets the angle. Yeah, so basically, if I want to rotate towards a point, I just put the two things here. Blah, blah, blah. So, if you're ever working with other people, make sure you write nice summaries. Like, I'm pretty much the only one who's going to be looking at this. So, like, I don't have to be that specific. So, but, like I said, I just wanted to know this exists. Because they're nice. Especially if you're working with other people. They don't have to keep asking you every time they want to know what you did. And be like, what does this function do? You could just write the summary. And it's nice. But, yeah. That's pretty much it. Yeah. That's all. That's all I got for you. I know this was a bit of... It's a lot to take in. Talked a lot about a lot of complicated stuff today. Like recursion. That's complicated. But list stacks and queues and static stuff, it's not that complicated. But I do want you to know that they exist because they're very helpful. I use them on almost a project basis. And by that I mean every time I work on a project, I use at least one of these at least once. They're very helpful instead of trying to jank up some system with arrays. Just like use a stack because it's already in the order you want it to be. And static stuff, honestly, I don't use them that much. I probably should use them more than I already do. But they're helpful because, as I said, any script can reference them. They're nice little things to have. But, yeah. And then summaries. If you're working with other people, make sure you put summaries. Also, as you can see here, I have a lot of comments. Well, this isn't a comment. I was commenting something else. That doesn't count. Okay, here's a comment. It tells me what this does. In case I just wanted to quickly look at it and be like, oh, what does this code do? Even if you're not working with other people, it's helpful. Because if you write a lot of code, you might forget what you wrote about 2 weeks ago. Just writing this little comment here is just like, oh yeah, this gets me the location. And then it adds it to the list. Well, the stack of whatever. Okay, that's that. I'm going on a rant again. But that's pretty much all I want to talk. Oh, actually I lied. There's one more thing. This is like a 5-second topic though. There's this thing called the region. And what it does is it lets you, whoa, look at that. It lets you minimize code. Whoa, it's great. You could also organize it. Like, you could also use them to organize code. So right here, I just have a whole bit of code that I commented out because I wrote the recursion function. And the recursion function works better than this monstrosity I had here. So I just put it in a region, and I could just hide it so it doesn't take up that much space on my screen. But if I ever need to reference this again, it's still here, but I want to just hide it. So what you do with a region, there's two things you need to know about. There's end region, and then just region. So what you do, type in, do the pound region, and then you just type in anything. So I'll just write the comment I have there. Check if currently in room. And then down here, you just do end region. And yeah, look, you can minimize it. Whoa. Isn't that crazy? Okay. I know I'm a bit excited, but as stupid as regions are, they're the best. I love them. It's so stupid, but it's nice to just be able to minimize your code. Okay, but that's all I want to talk about. Officially, that's officially the last thing I want to talk about. So, like I said, me and Natalie, or just Natalie, will be back on Wednesday. That's all I have for you today. Hopefully, you learned something useful that you could use in your projects. If not, I guess whatever. I see how it is, but you should have learned something new today. They're nice. I promise. You'll love them. Just use them. Just try to use them at least. But that's all I have to say. Bye-bye.